new on Curiosity Stream.
I'm James Burke. I'm going to take you on a journey through time.
James Burke's visionary series returns, reimagined for our time.
Now, this is all uncharted territory.
The Washington Post hails Burke as one of the most intriguing minds in the Western world. The New York Times raves he careens from one great moment in history to another.
Where do we want to go from here?
Experience all new connections.
So what's the next connection?
With monthly, annual, and bundled plans, find the one that works for you at curiositystream.com.
For the ones who get it done, the most important part is the one you need now. And the best partner is the one who can deliver. That's why millions of maintenance and repair pros trust Grainger. Because we have professional-grade supplies for every industry, even hard-to-find products. And we have same-day pickup and next-day delivery on most orders. But most importantly, we have an unwavering commitment to help keep you up and running. Call, click Grainger.com, or just stop by. Grainger, for the ones who get it done.
This is SpaceTime Series 23, Episode 86, for broadcast on the 24th of August 2020. Coming up on SpaceTime, the best place on Earth to see the stars. Dozens of brown dwarfs discovered in our local stellar neighbourhood. And the 10th group of Starlink satellites now in orbit. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has determined that a frozen plateau in Antarctica, known as Dome A, just happens to be the best place on Earth to see the stars. A report in the journal Nature claims this remote site, some 4,000 metres above sea level, has some of the most stable atmospheric conditions on the planet. Looking at space from the Earth's surface is a bit like looking at the sky from the bottom of a swimming pool. Atmospheric turbulence caused by local topography such as valleys, cliffs and mountains, together with differing temperature inversion layers, distort the incoming light from stars, causing them to twinkle. That's very romantic for lovers, but it's bad news for astronomers. Getting rid of that twinkle means putting telescopes on high mountain tops, above as much of the atmosphere as possible. Astronomers also use adaptive optics. This employs lasers to measure atmospheric turbulence and then uses that data to adjust actuators, making slight continuous changes to a telescope's mirror to compensate for the turbulence. Of course, you can get rid of all that turbulence completely by putting telescopes in space. But of course, that's hundreds of times more expensive than ground-based observatories, and there are limits to the size of any telescope you could get up there. So scientists have been looking for another option, one that involves finding a spot on Earth where the atmosphere is naturally less turbulent. And that's where Dome A, the highest point in the Central Plateau region of Antarctica, due south of Australia's Davis Station, comes into its own. After setting up a small telescope at the site, scientists found that the conditions at the plateau lend themselves perfectly to viewing stars with less interference from atmospheric turbulence than pretty well anywhere else on the planet. The 25-centimetre aperture telescope was placed on a specially constructed 8-metre high platform. The height of the platform was crucial because it raised the telescope above the steep temperature gradients near the surface. One of the study's authors, Professor Michael Ashley from the University of New South Wales, says the reduced twinkling means images are sharper and brighter. The Dome A plateau is almost dead flat for hundreds of kilometres in every direction, thereby making the atmosphere extremely stable. Ashley says the slow wind that does blow across the plateau is so smooth it generates hardly any turbulence. And what little turbulence there is restricted to a very low boundary layer. Ashley and colleagues used radar to measure the boundary layer thickness at Dome A, finding it to average around 14 metres and fluctuating from virtually ground level up to about 30 metres. The authors found that by setting up their telescope on an 8-metre platform, it protruded past the boundary layer about a third of the time. The telescope took an image every minute between April the 11th and August the 4th last year, obtaining 45,930 images taken when the boundary layer was lower than the 8-metre platform. The images were taken during what was the Southern Hemisphere winter, with no humans present, and the power systems, computers and satellite communications all operated remotely. Ashley says as well as being between 10 and 100 times less expensive than a space-based telescope, building an observatory on Dome A would also allow scientists to add new technology and service the equipment more frequently. In space, everything's delayed because you can't easily use a lot of modern integrated circuitry because it's not radiation hardened. That means even the best space-based telescopes are using technology that's lagging about 10 years behind what's available on the ground. And Ashley points out there's also a strategic advantage in Dome A. It's just 900 kilometres from the South Pole, which of course means that midwinter polar nights there are 24 hours long. All the more time to view.
Well, it's a remote location on the Antarctic plateau, and what we've shown with recent observations is that it's got the best seeing conditions on the planet. And seeing is an astronomical term which refers to how small the diameter of the star images are when you take a picture. So when you take a photograph of the stars or an image of the stars with a detector, from a normal site, the star's blurred out by the atmosphere. But when you go to Dome A, that blurring is a lot less, by something like a factor of 2.5. So the stars appear to be much smaller, which means that we have a higher resolution and we can also see fainter stars. Getting rid of that atmospheric effect as much as possible is something that astronomers have been doing for well over 100 years. So we've been searching for the best sites. Obviously, space is the ultimate site, but that is very costly and difficult. So next best thing is somewhere like Antarctica. And the advantage of ground-based astronomy is we can do things much more cheaply. The conditions aren't as good, but we can use the most up-to-date technology because we don't have it space qualified, which means that a sort of decade-long process to get space qualification isn't necessary. So, we can track the state of the art a bit more in terms of high-tech equipment, and if something goes wrong, servicing is relatively straightforward. So I think ground-based astronomy has got a very long future. Some types of astronomy, you have to go to space.
There are different parts of the electromagnetic spectrum which simply don't penetrate through the atmosphere.
Exactly. And one of those is terahertz, which is a region that corresponds to about a millimetre wavelength, and that is between the far infrared and radio part of the spectrum. And interestingly, that near Dome A in Antarctica, and that sort of region, is by far also the best place to do terahertz astronomy. And that's because the very simple reason, it's just that terahertz waves are absorbed by water molecules. So in a normal room in Hobart or Sydney or wherever, you couldn't see across a room if you had terahertz eyes, because the water molecules in the room would just absorb all the light. So you can imagine if you had terahertz vision, everything would be a haze. You could only see sort of typically 5 metres away before everything would fade out into sort of grey gloom. But at Dome A, the air is so dry that there's hardly any water molecules in it. So you can actually see all the way to the top of the atmosphere and then out into space. And it's just staggering. If you take a column of water vapour from the ice level at Dome A all the way to the top of the atmosphere and you get all the water out of the atmosphere in that column, it can be as low as 0.025 millimetres thickness of water. Now, you compare that to somewhere like Sydney where you get maybe a 10 centimetres thickness of water. It's a huge difference. And the reason for it is so simple. It's just that the air is so cold that all the water vapour has fallen out of snow and there's none left.
So a terahertz telescope at Dome A, for example, would fill the gap between something like ALMA and the longest wave infrared ground-based telescopes that are available. There aren't that many. Yes,
that's right. I mean, ALMA is also at a very good site, but Dome A is far superior for around about a terahertz. ALMA is good for a slightly longer wavelength, but when you get out to the terahertz, it really starts to absorb water vapour. So, for example, a rough comparison is that when you're at a terahertz in frequency, at Dome A, you can observe for something like 70 days a year when the water vapour is sufficiently good that you get good transmission. In ALMA, it's maybe 2 or 3 days. So it's really a dramatic difference in your observing efficiency by going to Dome A.
How do you observe in terahertz? Is it what we normally think of as a telescope with a mirror or in a lens, or is it one with a parabolic dish? Or
That's a great question. It's sort of between the infrared and the radio. So it's a sort of combination of both types of technology. You can actually use aluminium parabolic mirrors to reflect the radiation. You could do that with radio as well. You don't typically need to go to that level of accuracy. But the real problem is the detectors. We don't yet have very good multi-pixel detectors in the terahertz. It's still largely just using single element detectors and scanning them across the sky. So building up an image is a very slow process. You have to put your telescope with a single detector in and then just scan it to make up an image. So it takes a lot longer. We're talking factors of... Now, when you compare that with a CCD camera, which can detect millions of individual pixels, or tens or even hundreds of millions of pixels in one exposure, we may just do one pixel in terahertz. So it's very early days in technology, but it's starting to become available, and I think terahertz astronomy's got a very big future.
Is there much terahertz astronomy happening at the moment?
No, there isn't. And there are two reasons for that. Well, three reasons, I suppose. One is that the technology is just in its infancy. The other reason is that you can't do it from anywhere else really except Dome A and the tiny bit of the time in Atacama. And the third reason is just because of these first two reasons, there aren't any astronomers that know anything about terahertz astronomy. So it's not well understood by astronomers. Most people don't even think about it because they haven't been able to get their hands on any terahertz data. But I think there are a lot of very interesting astronomical emission lines in the terahertz, which we could study if only we had access to them.
I was about to ask you that question. Do we know what we're missing?
There are a few molecules and atomic transitions which do emit profusely in the terahertz. In fact, the strongest emission lines in the Milky Way galaxy are in the terahertz region. So extremely bright. And they have some advantages in terms of studying star formation regions where they act as traces of hydrogen molecules, which otherwise are very hard to see because they don't tend to emit when they're cold. So even though hydrogen is the dominant thing in the universe, when it's cold, you can hardly even see it. So some of these other lines, such as carbon lines in the terahertz, act as traces of hydrogen, which tell us a lot about what's going on in molecular clouds, which otherwise we wouldn't be able to work out.
That's why we use other chemical elements that we can see as surrogates, because we know that cold molecular hydrogen is associated with them.
Exactly. Carbon monoxide is the typical one that's used, and that's in the radio spectrum. But these terahertz lines have got some advantages over carbon monoxide. They probe different regions of the cloud, which gives you a better overall picture of what's going on. The other key factor is the atmosphere is very stable, which means that you can build what's called a terahertz interferometer. So you can put two terahertz telescopes separated by 100 metres, and you can basically turn them into one big telescope like you do with large radio telescopes.
Improve
you
your
can't do that anywhere else. The atmosphere is just not stable enough, and that gives you tremendous resolution.
Setting up a telescope system at Dome A, you'd only really be able to use it for less than 6 months of the year, but I guess that doesn't matter if you're looking in the terahertz area.
Yeah, terahertz you can observe all year round.
Yes.
Although it is drier in the wintertime when it's colder, so the terahertz is improved in wintertime. But you're right, the optical and more near-infrared telescopes would have to observe mostly during the 6 months of winter. But of course, then you get almost continuous darkness for at least 3 months. It's continuously dark. That's an advantage for quite a lot of astronomy.
That's the main reason for looking at Dome A for the terahertz astronomy. Would that be right? Because when I first saw this story, I was thinking to myself, well, wouldn't adaptive optics solve the problems of being able to see through the turbulence in the atmosphere? But from what you're telling me, it's not really that part of the electromagnetic spectrum that you're worried about.
You're right. When you go to optical and infrared wavelengths, you can use adaptive optics to get rid of some of the twinkle of stars. But that's a very complicated business, adaptive optics, and you're always much better off to start with better natural seeing. Rather than go to a poor site and try to fix it up with adaptive optics, you really want to go to the best site you possibly can and then use adaptive optics to make it even better. Because there are a lot of bad things adaptive optics does to an image. It squeezes the stars into different positions, and you end up distorting other regions, and the brightness of the stars varies depending on where they are. And you end up with a trade-off, which means that your images aren't really as good as they would be if you'd started off with better atmosphere in the first place. So at Dome A, we've seen median seeing of about 0.3 of an arc second, and occasionally 0.13 of an arc second, which is just phenomenal. And that's natural seeing, which means you could take a large, wide-field image and get those sort of stars over the entire image.
Tell me about Dome A, not too far from Davis Station, is that right?
Well, it's a fair way in from Davis. I'm not sure offhand of the actual distance. I think it's a bit over 1,000 kilometres from Davis Station. It's roughly between there and the South Pole. So it's a very isolated location. It's called a dome because it's the highest point in that area. In fact, it happens to be the highest point in the whole Antarctic plateau. It's 4,100 metres above sea level, and about 3,000 of those metres consist of solid ice, and below that is rock. So it's a pretty unusual place. And one amazing thing about the Antarctic plateau is how flat it is. It's flatter to roughly 1 part in 1,000. So if you walk a kilometre from Dome A, your elevation will drop by 1 metre. So that is very, very flat.
What's the weather like in that part of the world? Because when you think of Antarctica, you often think of how windy the place can be and the special training you need, not just to protect you from the cold, but also from the wind.
Yes, well, in the public perception, Antarctica is a windy place, and you have visions of Mawson and Shackleton and people heroically battling extraordinary blizzards.
Yes, I'm going outside maybe sometime.
Yeah, exactly. But the Dome A is the least windiest place on Earth. In fact, that's another one of its characteristics. And that's because it's right at the high point of the plateau, and that's where the winds actually start. And the winds in Antarctica are called katabatic winds. And they basically start right up at Dome A, and then they start to flow down from there as the cold atmosphere sinks onto the ice. And as they get further away from Dome A, they get faster and faster until when you reach the edge of the continent, which people who work at Dome A call the banana belt, the winds can easily exceed 100 kilometres an hour. But that is never seen at Dome A. I think the highest wind speed ever recorded at Dome A is something like 18 metres per second, which is sort of like a stiff breeze, basically.
Is it a place which is easy to communicate with? I mean, it's not somewhere you could have geostationary satellites overhead, so is it somewhere you can communicate with?
Yes, communicating is difficult. We use the Iridium satellite network, which is quite reliable, and we can transmit reasonable amounts of data. I guess maybe a couple of gigabytes a year, that sort of level, which is nowhere near the amount of data we'd like to send back. So we're only sending back reduced data and snapshots of the images, and we physically retrieve our hard disks at the end of each year. Now, I think in the future there are going to be some new developments. I was thinking, Elon Musk's Starlink satellite system, for example, may well be interesting from the point of view of transmitting data from Antarctica. I don't know the details, but I think there is a lot of interesting developments going on. And even with the CubeSat nowadays, it is possible to use sort of 5G modem technology to be able to transmit vast amounts of data CubeSat, which could then relay it to a ground station. So there are all sorts of exciting possibilities, but at the moment we don't have the bandwidth. Interestingly, it is possible to see some old geostationary satellites that have sort of run out of fuel and have drifted away from the normal geostationary orbit. And that's what they do at the South Pole Station, the American station, at -90. But it does require a large, like a 10-metre diameter dish to do the transmission of the geostationary satellite. And that is a pretty expensive operation. So we just use Iridium, which is a fairly small little modem, which works quite well.
How about a timeline for what you'd like to see and when?
Yes, a timeline. Well, we've been working in Antarctica since 1995, actually, and we've been working at Dome A since 2004. So it's quite a long time. We've been gradually building up our expertise, deploying larger and larger telescopes. They're sort of pathfinder experiments to prove that we can do it. And we're now at the stage where we are proposing a 2.5-metre telescope. This is a Chinese telescope called K-Dust, which I'm very excited about. And they have a companion terahertz telescope called Date 5, which is a 5-metre terahertz telescope. At the moment, it's under consideration for funding. So that would be extremely exciting. It's not a trivial thing to do by any means, but I think we're at the stage where something like that could go ahead. The station only operates for about 3, maybe 4 weeks a year over summertime. And the Chinese go in, they use a tractor traverse from the coast. They have typically something like 5, 6, 7 Caterpillar tractors pulling a series of sleds and shipping containers on sleds. And the people live in the shipping containers. They trundle along at about 10 kilometres an hour. It takes them 2 weeks to get to Dome A. They there then work for about 3 or 4 weeks installing equipment, and then they go home. Mm-hmm. And they're gradually building up infrastructure at Greenland Station at Dome A, and eventually it will be possible to winter over the whole year, but at the moment they're not doing that. It will be very challenging. Not just the cold, but also the altitude is pretty severe. It's 4,100 metres, which is seriously into the sort of altitude where you can get altitude sickness.
That's Professor Michael Ashley from the University of New South Wales. And this is SpaceTime. I'm Stuart Gary. Still to come, dozens of brown dwarfs detected in our galactic neighbourhood, and the 10th pack of Starlink satellites now in orbit. All that and more still to come on SpaceTime.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
Today's edition of SpaceTime is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
You're listening to SpaceTime with Stuart Gary.
A new study has uncovered 95 previously unknown brown dwarfs lurking in our cosmic neighbourhood. The findings, reported in the Astrophysical Journal and on the pre-press physics website archive.org, were made by citizen scientists using new NASA-designed software. Brown dwarfs are failed stars, objects which don't have enough mass to sustain core hydrogen fusion, the process which makes stars shine. While some brown dwarfs are born as such, others start their lives as spectral type M red dwarf stars, which wind up losing enough mass during their evolution to cease core hydrogen fusion, turning them from red dwarfs into brown dwarfs. Brown dwarfs fit into a category between the largest planets, which have about 13 times the mass of Jupiter, and the smallest red dwarf stars, which are on average around 75 to 80 times the mass of Jupiter, or less than a tenth the mass of our Sun. The newly discovered brown dwarfs include many within a few dozen light years of the Sun. These are our near neighbours. The discoveries were made as part of NASA's Backyard World's Planet 9 citizen science project. While some brown dwarfs have surface temperatures of many thousands of degrees, many of these newly discovered ones are colder than the boiling point of water. Some even approach the temperature of the Earth and are cool enough to harbour clouds of water vapour. Brown dwarfs with low temperatures are also small in diameter and therefore faint in visible light. Still, they do give off heat in the form of infrared radiation, and that can be detected by NASA spacecraft such as NEOWISE and the Spitzer Space Telescope. These newly discovered cool temperature brown dwarfs represent a long sought-after missing link within the brown dwarf population. Back in 2014, scientists discovered the coldest known brown dwarf, catalogued as WISE-0855, using data from NASA's WISE mission in infrared light. WISE-0855 has a photosphere, if that's the correct term, surface temperature of minus 23 degrees Celsius, and no other brown dwarf has even come close to matching this object's low temperature. In fact, some astronomers have warned that if 0855 might actually be a rogue exoplanet that was ejected from its host system. This new batch of brown dwarfs, together with others recently discovered using NEOWISE, WISE and Spitzer, puts 0855 into context. Principal investigator of the Backyard Worlds and citizen science officer Mark Kirchner from NASA's Goddard Space Flight Center in Greenbelt, Maryland, says these new discoveries help connect the dots between WISE-0855 and the other known brown dwarfs. The findings are also evidence that our solar neighbourhood is still largely uncharted territory. Mapping the coldest brown dwarfs down to the lowest masses also provides key insights into how low-mass star formation processes, while at the same time also providing a target list for detailed studies of the atmospheres of Jovian analogues. This is SpaceTime. Still to come, the 10th pack of Starlink satellites now in orbit, and later in the science report, climate change pushing Greenland's ice sheet beyond an irreversible tipping point. All that and more still to come on SpaceTime. SpaceX has launched its 10th Starlink mission, adding another 57 broadband internet satellites to the growing constellation. The launch brings to 597 the number of Starlink satellites now orbiting the Earth. The launch had been delayed several times due to both technical and weather-related issues. The flight aboard a Falcon 9 rocket from Launch Complex 39A at the Kennedy Space Center at Cape Canaveral in Florida also carried a pair of black sky Earth observation microsatellites.
Stage 2 box load is complete. Falcon 9 is in startup.
Call out. Falcon 9's in startup. Flight computers are now running the Falcon 9. We're pressurizing the stages for flight, and we're waiting for the final go.
LD, go for launch.
Stage 1 tanks pressing for flight.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. And liftoff.
Propulsion is confirmed. Merlin's look nominal. Power and telemetry are confirmed nominal from the avionics engineer. We're throttling down right now on the Merlin 1D engines, preparing for supersonic and max Q.
Mach 1.
Got the call out for Mach 1. We have throttled the Merlins back up to full power. Next event will be maximum dynamic pressure. And there we are. We're going through the thickest portion of the atmosphere at the highest speeds. Now as we continue to accelerate Falcon 9, the air density gets thinner and the loads on the vehicle decrease. Trajectory continues to look good.
Back dechill.
Back dechill indicates we're now beginning to bleed a little bit of liquid oxygen through the upper stage engine turbo pump to get it ready for ignition. The long plume coming out of the 9 Merlin 1D engines. Now major event coming up will be main engine cutoff coming up at just after 2.5 minutes called MECO. We shut off all the 9 engines. We'll separate the first stage from the second stage, and we will ignite the second stage engine called SES-1, the second stage engine start number 1.
Following main engine cutoff and stage separation, the Falcon 9's first stage returned to Earth, landing safely on the drone ship, Of Course I Still Love You, which had been pre-positioned downrange in the North Atlantic Ocean.
MECO.
Stage separation confirmed.
And we've got successful MVAC full power ignition. The MVAC engine, the second stage, now taking over, carrying the Starlink and Black Sky satellites to orbit. The first stage is continuing without power to coast to apogee. The large titanium grid fins beginning to open as we slowly head up the eastern coast of America. Now, next coming up will be fairing separation. And we confirm fairing separation. So the Falcon 9 second stage continues at full power, carrying the Starlink and Black Sky satellites to the first of 2 orbits. The first stage is continuing to coast to apogee, and then it will begin to fall back to Earth, and eventually 2 burns to land on the drone ship in the Atlantic Ocean. The trajectory right now continues to look right down the middle. Everything's looking good on Falcon 9.
Stage 1 is headed back home to Earth, and it will do this by executing a series of 2 burns. The first burn is the entry burn, where 3 of the 9 M1D engines will light up and slow the stage down as it re-enters the upper part of the Earth's atmosphere. The second burn is the landing burn, and this is a single engine burn that brings the vehicle speed down rapidly in order to land on the drone ship. The second stage MVAC is still glowing and in the middle of its burn there, carrying our satellites to orbit. Stage 1 is currently navigating home to Earth using both its grid fins and a nitrogen burst from the attitude control system, which is nitrogen gas that helps to orient and guide the first stage as it heads home. There are 4 grid fins and 4 attitude control thrusters on the inner stage of the rocket. We will hear the call out for the start of the stage 1 entry burn. This burn will last 20 seconds. Again, it's a 3-engine burn that will slow the first stage down as it enters the upper parts of the Earth's atmosphere.
Stage 1 entry burn startup.
Heard confirmation of the stage 1 entry burn startup.
Stage 1 entry burn shutdown.
We've had confirmation of successful stage 1 entry burn, and we're about a minute away from our landing burn. The landing burn will start at T+8 minutes, and it is also about 20 seconds long. The landing burn should bring us to our drone ship. Of Course I Still Love You in the Atlantic Ocean. Stage 1 is transonic right now.
Stage 1 landing burn.
Heard the call out for the start of stage 1 landing burn.
Stage 1 landing leg deploy.
Stage 1 sitting on our drone ship. Of Course I Still Love You.
SECO.
We've had confirmation of second engine cutoff, and we're waiting for confirmation of good orbit out of this first burn here.
Nominal parking orbit insertion.
The same Falcon 9 first stage had previously been used to launch the Crew Dragon 2's first demonstration mission to the International Space Station last year, as well as the RadarSat Constellation mission and both the 4th and 7th Starlink missions. The Black Sky Global satellites were deployed into their orbits about an hour after launch, while the Starlink satellites were released about 30 minutes later. SpaceX plans to launch an initial batch of 1,584 Starlink satellites, with long-term plans to launch some 42,000. Each 260-kilogram Starlink satellite is equipped with Ka, Ku, V and E-band transponders. The satellites are being placed in orbital shells at altitudes of 340 kilometres, 550 kilometres, 600 kilometres and eventually 1,110 kilometres high. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new study warns that climate change may have pushed Greenland's ice sheet to a tipping point that has set it on an irreversible path to completely disappearing. A report in the journal Nature claims snowfall that normally replenishes Greenland's glaciers each year can no longer keep up with the pace of ice melt. The findings by scientists from Ohio State University means that the Greenland ice sheet, the world's second largest ice body after Antarctica, would continue to lose ice even if global temperatures stop rising. The study's conclusions are based on a review of more than 40 years of monthly satellite data from more than 200 large glaciers draining into the oceans from across Greenland. A new study warns that the common high blood pressure drug hydrochlorothiazide has been linked to an increased risk of developing skin cancer among older Australians. Research by scientists at the University of New South Wales and reported in the journal Basic and Clinical Pharmacology and Toxicology shows that the drug contains photosynthesizing properties that can make skin more sensitive to the sun. The findings are based on a big data analysis of skin cancer rates in a case-controlled study among older Australians. The results support similar findings from previous international studies. Researchers found an increased risk of developing malignant melanoma as well as squamous cell cancers of the lip with hydrochlorothiazide use, and the risk also appears to be cumulative. That is, the longer that hydrochlorothiazide is used, the higher the risk of developing lip cancer. High blood pressure or hypertension is a chronic illness affecting more than a third of all Australians over the age of 18. It's usually defined as having a blood pressure level above 140/90. If left untreated, hypertension can lead to serious health conditions, including stroke and heart disease. Scientists have worked out how to turn house bricks into batteries. A report in the journal Nature Communications claims conventionally fired house bricks can be converted into a type of energy storage device called a supercapacitor that can be charged to store electricity to directly power LEDs. Researchers say the work could inspire the development of other multi-purpose construction materials in the near future. Archaeologists have unearthed the remains of a 2,700-year-old administrative centre in Jerusalem. The ruins date back to the times of the Jewish kings of Judah and Israel from the 8th and 7th centuries BCE. There are signs that governmental activity managed and distributed food supplies not only for storage, but also administered agricultural surpluses, amassing commodities. The scientists from the Israeli Antiquities Authority also unearthed a collection of 120 broken clay jar handles with seal impressions. The impressions contained a sun disk flanked by 2 wings and Hebrew writings naming the king of the period, names of one of 4 ancient cities from the Kingdom of Judah, and the names of senior officials from the period of the first Jewish temple. Scientists say the site was once dominated by large agricultural plots and orchards of olive trees and grapevines, which included agricultural industrial facilities such as grape presses for winemaking. It appears the site was abandoned with the destruction of the Kingdom of Judah and the exile of the Jewish people to Babylon in the year 586 BCE. One of the oldest and most persistent paranormal beliefs is that dogs have the ability to see ghosts thanks to some sort of sixth sense that dogs are supposed to have. A recent poll of over 1,000 pet owners in the United States found that, among other things, 47% of dog owners report that at one time or another their dogs had alerted them to some sort of impending bad news. These include behaviours like trying to hide in a safe place, whining or whimpering, hyperactive or erratic behaviour, or barking persistently just prior to something bad happening. But does that necessarily mean ghosts? After all, in reality, dogs have acute hearing and an acute sense of smell, which means they can detect a world of information far beyond the ability of humans. Infrasounds generated by earthquakes shortly before the arrival of the Trembler's first PNS seismic waves are a good example of our four-legged friend's early warning system at work. So there's nothing supernatural about that, it's just heightened senses. But as Tim Mendham from Australian Skeptics points out, if you believe in the supernatural, you're naturally going to think your dog does too.
There are people out there talking with pets. There are pet psychics, people who can sort of talk to your pet and therefore figure out if there's anything particularly worrying them. And I would presume that would also be the case of asking them if they can see a ghost. So I don't know what language dogs speak in their head, and I don't know if the psychics can speak dog. And dogs seem to be the one that they're always talking about rather than cats or goldfish.
Well, cats probably can see ghosts but don't care.
If the ghost feeds them, they'd be happy. Well, the thing is, though, someone suggests to take note of your dog's activity and to see if they are seeing a ghost, and one of them is staring intently at a certain spot. Your dog might bark or whine or growl or snarl or cry or whimper if they see something out of place. I know dogs that have dreams, of course.
Oh, all dogs dream.
Yes. Yeah, and you can see them.
Also, the cats, they dream.
But I mean, it's an interesting situation. Therefore, dogs do bark and whine and growl just off their own bat when they hear a noise or something, and they might have good senses to noise, etc.
As well as that, you've got to remember their visual range is different from ours. They see more in the infrared than humans do, so they're likely to be seeing things that you don't see anyway.
That's right. But apart from that, how can we tell?
Another example are cats. Cats actually see things that aren't there. I guess it's the ultimate form of pareidolia. They have very bad short-range vision, but really good long-range vision. But in the middle there, they tend to be seeing things which, upon closer examination, isn't what they thought it was. It's a piece of dust or something. They get really embarrassed and end up cleaning themselves. But they see things that aren't there a lot of the time. And this could be the same with dogs.
It could be the same with people too, of course. People see bits of dust and think they're in a photo, and they think it's a ghost, etc. But they don't then go and clean themselves. They don't lick themselves all over.
Now I'm picturing it.
No, don't. But I mean, honestly, this is a story that really, how can you tell? Unless you get someone who's, this story quotes psychics who've written books about dogs and pets and seeing ghosts and that sort of stuff. But do you trust the psychic is the question.
Well, my friend's often taken his dogs to the cemetery for a run there, and none of them have ever come back feeling haunted.
But they might come back with a bone.
Oh, I hope not. That's Tim Mendham from Australian Skeptics.
And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from SpaceTimeWithStuartGary.com, or from your favorite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through SpaceTimeWithStuartGary.com for all the details. If you want more space time, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.